So we have agreed that we are going to now learn about and solve the Einstein equation, which in the last lecture I presented to you was equal to this Einstein tensor equals 8 pi times the stress energy tensor. And we're doing this in my order, which is not the normal order. But the normal order would be, of course, to teach you exactly what this is and teach you exactly what this is, and then go ahead and proceed to solve. And that makes perfect sense, and I'm not suggesting that my order is particularly logical. But what I'm going to begin with is forcing the answer, structuring the problem in a way that forces space-time to be spherically symmetric. We're going to start with that. And then from there, we're going to impose that spherical symmetry requirement on this equation, and that's going to derive a solution to the Einstein equation that is spherically symmetric. So we can actually understand how to force this guy to be spherically symmetric without fully understanding the parts yet, right? This is a fascinating and super important concept in general relativity. You cannot proceed without having a good understanding of it. Likewise, this is true. This is as well. You've got to understand the stress energy tensor. Nothing makes sense. And we're going to get there, but the typical way is not necessarily my way. It's sort of insignificant, as you'll see in a moment. But I want to start by going through this process, forcing the spacetime to be spherically symmetric. Then you kind of learn something about the guts of this thing, even without our total understanding of what the Einstein tensor is and what the the energy momentum tensor is. Now, remember last time I said, okay, we're going to do this in a vacuum, and whatever the energy momentum tensor is, there is no energy and there is no momentum in the vacuum in the classical theory of general relativity. So that we're just going to set equal to 0, right? So that's the easy sort of hand-waving fix. Although I got to say, it's not too hand-waving. It's real, right? It's the real deal. It doesn't matter how we calculate, define, identify, measure this thing. If we're talking about the vacuum, then that thing is going to be 0. So that's accept that, and we can now move on to this guy. And I said, well, this guy, we're going to break it down into some very important tensor called the, this is called the Ricci Tensor, minus 1/2 times the metric of space-time times r. Now you'll remember what we said before about the nature of what we mean to say space-time. This is a really important point. I've said it before. Happy to repeat it. When we say we are going to force space-time to be anything, we can force space-time to be something, we can discover what space-time is, we can calculate a space-time. All these words, calculate a space-time, all these words you might ever use that precede space-time, whatever those words are, you might as well replace space-time with the word metric, because that's ultimately what space-time is. It's the metric. When we talk about things in space-time, we're talking about the geometry of things. Geometry. Where are things? Where do things live in relation to one another? How far apart are they? How fast are they moving? Geometry does not exist on any manifold, on any coordinatizable space unless you have a metric. So when we are forcing space-time to be spherically symmetric, we are actually forcing the metric to be spherically symmetric. You replace space-time with metric. That's what you do. They are one and the same concept. They are literally meaningless without each other. You can talk about space-time all you wish, but if you're not talking about it with a mathematical metric, then you're just being a philosopher. You can talk about the metric all you wish, but if you don't describe it in terms of space-time, it's an abstract mathematical quantity, just of unique interest in its own right, but it's not particularly applicable to physics. This is the mathematical entity, and this is how we interpret the mathematical entity and to understand physics. So when I'm going to force space-time to be spherically symmetric, I'm forcing the metric to be spherically symmetric. Okay, but what about this guy here, right? It's okay, so I can say I figure out a way to force the metric to be spherically symmetric, which I'll demonstrate soon. what about these two guys? How do I enforce spherical symmetry on the equation? And upcoming lectures, I'm going to talk about the Riemann curvature tensor in huge detail. And from that, we will immediately learn what this guy is, the Ricci tensor. And from that, we will immediately learn what the curvature scalar is. They'll all flow from one from another. This is a contraction of the Riemann curvature tensor, and this is a contraction of this guy. So it's going to be trivial. I have to show you first what the Riemann curvature tensor is. And ultimately, when we do that, we will be able to calculate the Riemann curvature tensor. It will be given in terms of the connection, which should be no surprise. If this is going to somehow be the curvature, right? If this is going to somehow be the curvature of space, then the object that tells us how the geodesics are laid out in space is certainly going to be a relevant part of it. So what would such an expression look like? So what I will show you in an upcoming lecture is that the Riemann curvature tensor is what we might call a rank 4 tensor, but it's really a rank 1-3 tensor, as I've written it here. And it is, and it can be expressed in terms of the connection. And this is the definition that we will uncover in a future lecture. It's an important thing to understand. It looks like a mess, but as with all of this stuff, you just work through it and you'll come to an understanding why this important tensor, its components, remember, this is a tensor components, and the components of that tensor are equal to this. And you'll notice you can check this. This is a tensor, so everything has to be ordered. So we have rho, sigma, mu, nu. And here we have rho, and downstairs we have mu, nu, and a sigma here. And in the places where we have more than just 4 indices, you'll notice we have a summation on the inside. So we have rho, mu, nu, and sigma. Likewise here, we have a summation here on lambda. In both cases, we're summing over lambda as a dummy index, and we have rho, sigma, mu, nu. So this is a 1-3 tensor, and therefore we have to understand it as rho, sigma, mu, nu, and then this is in the coordinate basis, right? The coordinate basis, so it will be the tensor product of those basis vectors times dx sigma, tensor product dx mu, tensor product dx nu. And we understand this. You've got to understand the principle of what this thing is. This is just a 1-3 tensor, and we've gone through the nature of tensors in our previous lectures. Here we start applying it. But notice the irony. I went on and complained, well, these books, they don't write out the basis vectors. They don't include the basis vectors. All they give us is this, and it's so confusing. And I whined about it, and you'll see throughout that entire lecture, I always keep the components with things. But you know what? Now that you all understand that, now that you've heard my complaining, ironically, I'm going to do what every general relativity textbook does. I'm just going to talk about the components. Because now you can see there's no ambiguity. You've got rho, sigma, mu, nu in order, right? That slot there, down here, this empty slot right here, that empty slot enforces an order. It enforces the rho, sigma, mu, nu order. So you know that when you look at this thing, you're actually looking at the component of a 1-3 tensor, and this is always the basis. The basis matches up and down with these indices. So as long as you keep ordering these indices correctly, this is entirely redundant information. And that's the whole point. So the point of that what is a tensor series is to get us here where we can start using the regular notation you see in books, but in your head you're always carrying around the fact that this is the component of a vector that lives in a 1-3 tensor product space. It lives in the tensor product space 1-3, and it is a simple vector in that tensor product space. And these guys here are those basis vectors. A little more review. If you don't understand that part, what I just said, that means you haven't done the what is a tensor series, and you're probably, well, you could still be, I mean, if you understand what this is, that's all that really matters. Then the other point to remember, of course, is that as such, as a tensor, rho, and I will never write this down because it is presumed that this is a tensor field. So it is a function of space-time, where this is actually a space-time coordinate, x0, x1, x2, x3. So this component is a function on space-time giving you a tensor product field, right? I can just put x, little vector up there, except the little vector arrow sometimes means 3 dimensions. So I could put x alpha, just give it another little component up there, x alpha if I wanted to. So I could say that this is rho, r rho sigma mu nu of x alpha, like that, to indicate that the argument of the tensor product field is space-time itself. So, and what does that mean? That means, of course, at every point of space-time, you can calculate a tensor that has this basis that's located at each point in space-time, and you can calculate the value of this tensor at every point in space-time. Okay, but the point of this is I'm showing you a formula that we will eventually derive. But the reason I showed you this is to show you something else. And the first thing is I got to remind you about these things in a physical space-time. So remember this thing? Remember that the connection on a space-time with a metric is given through this expression here. And we worked really hard to calculate this, but we finally got there. The point is this guy here is expressed entirely in terms of the metric and first derivatives of the metric. These are all first derivatives. By the way, both of these can be written in more standard notation. In fact, let's do that, right? Let me just, for the heck of it, I'm going to now write this down in terms of the exact same thing, but in terms of a slightly different notation. First, here you see the Riemann tensor that we'll learn about later. Now, instead of pushing partial u and getting these two first derivatives here, I use the single line and I put the notation here in the back end. So this is actually the index structure of this term. This is actually better notation in general. Now, these two terms don't change at all because there's no derivatives. But I can actually do the same with this, right? Here is a derivative term. I can put a slash k and a slash j here, right? So what I would do is I would erase this. And, well, maybe I should erase the whole thing. And then I would go G, R, J, single bar, K. Remember, the single bar just means a normal derivative. If I used a double bar, that would mean a covariant derivative, which is a far more interesting and complex entity. This guy, I'd get erase again, and I would write G sub R, K, J. And this makes sense because remember, by taking the derivative of things, you're actually increasing the rank of the object. Anyway, the point is that this guy here, this critical thing that is such an important part of the Einstein equation, in fact, it makes the bulk of the Einstein equation, can be written entirely in terms of the connection. And we're going to see how that's done and why in an upcoming lecture. But each of the connections can be entirely written in terms of the metric. In fact, this is better. So the connections can be written in terms of the metric and the first derivative of the metric. And then the Riemann tensor can be written in terms of the connections and the first derivatives of the connections. So buried in these terms are going to be second derivatives of the metric. So in the end, I can take so with that in mind, I can now define the Ricci tensor, R sigma nu, to be the contraction of the Riemann tensor, lambda sigma lambda nu, right? So I contract on these two indices together, lambda and lambda, and then I get the Ricci tensor, which is what is on the left-hand side of the Einstein equation. It's buried here in the Einstein tensor. The Einstein tensor is literally defined by this. In case you don't remember from last lecture, G mu nu equals this Ricci tensor minus 1/2 the metric times this curvature scalar. So once I explained to you the Riemann curvature tensor, which is, again, an upcoming plan, you see that a simple contraction of whatever this object is gives you this left-hand side piece of the Einstein tensor. That's this guy. And then I can also tell you that the curvature scalar itself is going to equal r lambda lambda, which is the contraction of this guy. But of course, you can't just straight up contract that guy. When you see r lambda lambda, you have to think automatically g sigma lambda r sigma nu, like that, right? G symmetric, so I guess I could also write it g lambda sigma r sigma nu, depending on whether or not you like. It is best to have the contracted indices sort of near each other, but this is what that means, right? Whenever you see, contracting this guy, you can't contract two lower indices together. You can remember that from our What is a Tensor series about contraction. But you can raise it and then contract it, and that's what the definition of R is. The point is that this is entirely in terms of this, which is entirely in terms of the metric. So this is entirely in terms of this. So this is entirely in terms of the metric. And this is defined entirely in terms of this, which is entirely in terms of this, which is entirely in terms of this, which is entirely in terms of the metric. So the point is that when you write down the Einstein equation, when I write down r mu nu minus 1/2 g mu nu r equals 0, this entire side, is really some weird function f of the metric g mu nu, the metric's first derivative g mu nu slash, say, lambda, and its second derivative g mu nu slash lambda, so let me give you an alpha, right? Remember that you might be tempted to put 2 bars for a second derivative, but that's wrong. That's the covariant derivative. You just, multiple derivatives, you just string them along after the line. That's not used much. You don't see that too much in the notation. It'd be much more likely to see g lambda, alpha partial, not g, partial alpha, partial lambda, g mu nu, right? That would be the second derivative. The point is that there's a function of the metric's first derivative, and the metric's second derivative, and that equals 0. Therefore, the reason I went through all of that is to show that ultimately the Einstein equation is ultimately an equation about the metric alone. But it's so intricate. I mean, imagine this, right? Look what you've got. Just to figure out this term, you got to take the derivative of this thing. So this term here, this term right here, is the second, it has second derivatives of metrics that are contracted with each other. And remember, these contractions are components being multiplied out. I mean, imagine you tried to write this whole expression. Imagine you tried to write this expression here entirely in terms of the metric. First, you would have to substitute this in for every component here and rewrite the indices. Rewrite this j, r, k in terms of whatever is relevant, rho, mu, lambda, right? That's the first thing I'd have to do. Rho, mu, lambda, I'd have to put it in. I'd have to reshuffle them in the right order. This one has its order, this one has its order, this one has its order. I'd have to shuffle all of these indices around. Then I'd have to take these derivatives. Right? I'd have to take these derivatives. I could easily, it's funny because this notation is more comfortable. I want to point to this derivative. I can point to this whole partial mu. It's a little bit more annoying to point to this bar here. Same thing though. So I have to take these derivatives of those substituted things. All right, fine. But then I have to then take all that expression. Imagine how long it's going to be. It's going to go way, way out here. It's going to be huge expression. Then I'm going to have to execute this contraction. So then I have to contract all that stuff. And then I have to save what I get, and I'll get 16 components when I'm done, right? Because this is 4 and 4. I'll get 16 components. And then on top of that, I contract it again with yet another application of the metric here. And I contract it again, and I get R. So everything I had up here or here is going to get doubly jammed up and summed just to get this number R, which seems like, hey, this is just a scalar. But imagine the expression for this scalar, right? I'm now contracting something that it was already a huge mess to begin with. And then when all that's done, I go back, multiplied by the metric again, the scalar part, multiply by half, subtract component by component. So remember, this is still going to be R00 minus 1/2 G00 R, right? But buried in R00 is going to be all these G00, G01, G02, G03, G10, G11, G12, G13, all the way to G30, G31, G32, G33. The only one I didn't do is, heck, why not? G20, G21, G22, and G23. So there's all the components of the metric, right? And of course, there's symmetric, right? The metric is symmetric, so G33 and G03 are going to be the same. So thank goodness for that. But in the end, all of those things are, but R00 is going to have all these components in there. So that's not much of a simplification, but I have to calculate R00, R01, R02, R03, and then R10, R11, R12, R13, etc., etc., etc. And then, so I'll have 16 of those. So I'll have 16 things on this side. 16 things on this side of the equation. It's 16 separate equations, right? So, but in the end, even though it's written this way, the point I'm trying to make is it's all in terms of the metric. And why am I going to such a big length to show that? First of all, it's because a lot of students miss that point out, that you're solving for the metric. A lot of students go through GR and they kind of never really figure out that that's what it's all about. That's the whole name of the game. But that aside, now when I go back to this original demand, forcing space-time to be spherically symmetric. Well, this equation here that has all of this in it, it's asking a simple question. What is G, well, let me do my simple question in red. What is G mu nu? What is G mu nu, right? That's all you want to know. What is the metric? When you say I'm going to solve the Einstein equation for a space-time, that's what you're asking for. And now it's evident. I'm looking for the right metric that equals 0. But there's a lot of metrics and a lot of expressions that will equal 0. The ones that matter are the ones that have this exact form. And they're all going to be vacuum solutions. We forced them to be vacuum solutions because we've already thrown out the right-hand side, basically because I didn't want to talk about it. I'm not smart enough to talk about spherical symmetry in the presence of a matter field. That's not what I'm interested in because it's too hard. So I just threw out the right-hand side, leaving me with this. This is an equation for the metric. So that's what we're trying to do, is solve for the metric. And we're solving for a spherically symmetric space-time. So now that means in the end, this guy had better be spherically symmetric in the end. So let's talk about what that means. And we are going to look only for solutions that have spherically symmetric metrics. And that's the answer to this beginning part of the lecture, which is when I say I'm going to enforce spherical symmetry on space-time, what it means is I'm forcing spherical symmetry on the metric. So now let's talk about how to do that. All right, so we begin with the actual metric itself. We know it's a rank 0-2 tensor. This is our basis vector part. This is the components, which are a function of space-time. And what this is telling us is that if we lay out coordinates on space-time, where maybe this is x0 and this is x1, and then there's x2 and x3 out there, At every point in space-time, I can calculate g mu nu at the point P. Let's call that the point P. We'll call that one, say, the point Q, and I can calculate g mu nu at the point Q. So every point in space-time has its own components for the metric. And this, of course, represents 16 different values, right? G00 at Q, G01 at Q, and ultimately this object, g mu nu at Q, is a rank 2 tensor that lives at that particular point, in this case Q, at spacetime. And this is true for every single point in spacetime. So that's what we're after, this metric tensor field. Whoops, sorry. Metric tensor field. Now, if you studied many relativity books, you'll notice that when they talk about the metric tensor field, they just write g mu nu. And I kind of went through that in the previous discussion about the Riemann tensor, that we're going to start leaning on that. We understand that this is a function of space-time. We don't have to say that anymore. We understand that that is the component of a tensor. We don't need to put the components on because we know these indices down here automatically tell us that the components have the superscript indices and are these component or these particular basis vectors of the dual space. We understand all of that. So we don't have to write it down anymore. And we are now going to lean on the method of most of the books that are out there, which is to just do everything in terms of the components. Now, another thing, though, you'll see in a lot of textbooks is this statement. ds squared equals g mu nu dx mu dx nu. And that is something I want to make sure we have absolute understanding on, because before we can do our spherical symmetry, we have to understand how do we link this concept here, the concept we've worked on, with this concept here. And the method is, well, the logic is not very difficult. What we're going to understand is that the metric in abstract terms, and I shouldn't say abstract terms, everything here is somewhat abstract, but we have the coordinate notation, which has these indices, and then we have the coordinate free notation, which doesn't. And normally this would be some kind of bold letter if you're doing coordinate free. So if there's the metric, all you know is that it takes two vectors and it gives you a real number. So it's an object that has these two slots that are waiting for vectors. So what do? Well, we go to this point in space-time, and because it's a manifold, what we're going to say is we're going to put in a vector that is at that point in space-time. We'll call that vector d. But it'll be a short vector, and its intent is, actually, let me put d at q. Let me put d right here at q. I'll also do it in green. D is here. It'll be a very short little vector, and its intent is to point from q to a nearby point. Now, we know that this vector d, I better label it, this little vector d, that vector d lives in the tangent space at q. It doesn't really point to, it doesn't really connect to these two points in space-time, because space-time is not the vector space that d lives in. D lives in the tangent space at q. But because everything is a manifold, if I bring this point really close to q, I can approximate a line that does go through space-time that connects q to, I better give this thing a name, this point here, oops. This point here we'll call, I better do it in red, oops. This point here, we'll call that point S. And so a little vector from q to S, right, that doesn't even make sense to say a vector from q to S, because vectors live in the tangent space at q and the tangent space at S. If I bring these two close together, though, what I can say is that the tangent space of q approximates, I can approximate a little connection between q and S with a vector d. And now my question might be is, well, the vector d that approximates the displacement from q to S when S is close to q, well, what am I going to call that vector? And so I would write down, let me erase some stuff here. I'm going to call this vector d some component delta t times the coordinate basis vector of in the t direction, some component delta x times the x basis vector, some component delta y times the y basis vector, and some component delta z times the z basis vector. Alternatively, I could write it this way, some component of x0 basis vector 0, x1 basis vector 1, x2 basis vector 2, and x3 basis vector 3. I could write it that way as well. Here I'm replacing x0, x1, x2, and x3 with t, x, y, and z. You should be able to go through both of these things. I've called this vector d, but that's just the name of d. It is not to be confused, of course, with this or with the exterior derivative. It's just the name of this little vector. And so I can take d, this little vector that I'm going to use to just approximate this separation. I can put that in here, d and d. And out I should get the magnitude of d squared. So let's actually calculate this guy. You know what? Actually, let me change something around, because d is going to be a dangerous name. If I call it d, you're going to get confused with those d's I just mentioned, and it's not going to tie into this s at the end. So let's call it s, right? S, S, S. This little distance is s, and this point here, we'll call that QP, we'll call that point R, so QR. Because ultimately I want to show you what ds squared is in so many of those textbooks. So I got to name that little thing s. Anyway, so I put in s and s here, and what I should end up with is essentially what we would call s squared, the magnitude of s. So now let's calculate this. Let's actually calculate this using the notation, using the standard abstract. I keep saying abstract because that's really the wrong word. In the coordinate-free notation. So I'm going to write down this expression in the coordinate-free notation. So step one of that calculation is just take s and s here and substitute the full-on the component form of f and s of s and s. So this is the component form of these two of this little displacement s. And then this is g operating on these. There's a comma here. That comma is that comma, and then it repeats below. So that's s and that's s. Now I just use linearity and blow this thing up. Linearity means these pluses can be separated and these constants can be pulled out front. So what happens when we do that? Okay, I hope I got this all right. It's not hard, right? Because you're just expanding. You're taking this 4 terms and multiplying by that 4 terms and just blowing it up. So, you know, for example, this term times this term is going to be delta x0 squared, to delta x0 from there and from there. And then what's left behind linearly is g acting on the 0 basis vector and the 0 basis vector itself. Then this term, the next term will be this term multiplied by this guy, which will bring out a factor of delta x0, delta x1 in the front, and then g times the 0 basis vector and the first basis vector. And you just proceed, you get delta x0, delta x2, g12, delta x0, delta x3, g03, and you just blow it all up. And so you get all of these terms. And so, I mean, what do you do for these terms? Well, the next step is going to take each of these terms and figuring out what are those terms. When I say g13, what do I mean by g13? Well, that's not hard, right? Because we know the form of g. G is always going to be this guy, right? G is going to be that guy. And we know in the coordinate basis, these are those basis vectors, and they're designed such that dx mu partial nu equals delta mu nu. It's a real number, right? These are maps that take vectors and give you real numbers, and this particular set of maps is defined so that this map, this particular one form, dx mu, operates on the basis vector of the vector space to give you the delta function. That's how they were defined in the dual space mapping. It's the dual to the basis, right? And so that makes these relatively easy once you substitute for G this form. So let's do that. Let me move this up for a moment. So the first step of that process is you take our coordinate-free notation. This is actually a blend because we obviously have coordinate notation jammed into here. So as soon as we made this substitution, we were kind of leaning into coordinate notation. We just hadn't made it for this guy. We only made it for the arguments s. Now we're making it for both. We've done it for the arguments s. We've blown it up. So for example, this term here, which is this first expression here, now I substitute the full summation with the mapping in it as a place for G, and now I have this tensor mapping this vector, which is very simple to calculate, right? The mapping consumes these two maps. These two maps consume these two vectors, giving you these real numbers. So that's the dual space mapping of a basis vector and a dual space mapping of a basis vector. So these guys end up being delta functions. And you get this almost trivial answer, right? These delta functions enforce mu and nu to equal 0, and you get G 0, 0. So this actually is, and this should be no surprise, this is the definition of the 0, 0 component of the metric tensor, right? And that's what you get, the 0, 0 component. So this first term here, right, this first term here, which is delta x0 squared, it ends up being replaceable. We can replace that with delta x0 squared g 0, 0. And this logic applies everywhere. Let me just do one more example just to make a mixed one clear, and then we'll just make the substitution for everything. So the next example we'll do will be g partial, say, 1 partial 3. You know, just sort of separate them out a little bit. But we write the same thing we did before, g mu nu dx mu, because it's the exact same process. X nu operating on these two basis vectors now, and you end up with g mu nu, and I'll skip a step and I'll go delta mu 1 delta nu 3, which equals g1 3. And therefore I should be able to go here to, where is it, this term here, and I can write this is actually equal to delta x1 delta x3 g1 3, right? And likewise, I can substitute everything out and using that same technique and rewrite this entire expression. I can rewrite this whole thing in terms of the metric components, right? Because that's what these are. These are the metric components. You just have to kind of work through this long chain of mathematics that we've learned pretty aggressively in the past in our other lectures, and you get there. So what does this guy here, what does all of this, maybe I should make it permanent, what does all of this look like after you do that? All right, let me show you. Okay, I wrote it all out. I tried to be very neat about it, but you know, the pattern is pretty simple. I mean, I've just substituted the metric tensor component for these coordinate-free pseudo-coordinate notations over here, and we just get g0, 0 times delta x0 squared, g0, 1 times delta x0 delta x1, g0, 2 times delta x0 delta x2. Now you got to go back and remember, what are these delta x's? Remember that the idea behind the delta x's is they were the coordinate expansion of this little guy s. And that little guy s was supposed to be a tiny displacement vector that connects two very nearby points in space-time, which I am referring to sort of the old calculus form of delta. When I put in this delta here, that's like from calculus, right? When we were starting to talk about a small increment of something, that's what this is supposed to mean, a small increment of something, where small is defined in some very specific way, but here it's just limited to how accurate you want a little vector to connect 2 points in space-time. So once we've done that, we have the small vector implied by these deltas, and now we have these small vectors here, and that is the magnitude of this little displacement vector s. And so now you do the final step. Remember, the goal of all this was to understand this expression here. And this expression here, there's two reasons it's confusing to people. One is we go on and on about how these differentials here are not really differentials. We talk about them as one-forms. They're dual-space tensors. But when you look at it here, it's kind of hard to see it that way. But in this case, it literally means that, because you're talking about a real number, right? This is a number, right? This is a small increment of space-time. The squared distance between 2 points is what books mean by this, right? This here is not a tensor. Therefore, this is not a tensor. This is not some sort of shorthand for dx mu, dx nu. And that's the problem that people have got to understand. Actually, my work to show what this means here, all that work can actually cause confusion when you look at this thing. So what is it then, if not that? Well, look at the sides of things. This side is meant to be a number, a small amount of something. So this side is the product of a number times two small amounts. These are true calculus differentials here. And where do they come from? Well, over here, we end up with this, which is actually the metric applied to a vector, which is a real number. And in fact, it is the magnitude of s squared. It is s squared. S squared equals g mu nu delta x mu delta x nu. And now the summation convention is back, right? All of this is just the blown up version of this. You sum over mu, you sum over nu. Let me write that. And then is the last step almost becomes obvious, right? You let delta become infinitesimal. And now we're using this d in the context of regular calculus. So we have delta x mu is dx mu. And now we're talking about infinitesimal vector components. And this will allow us to take both sides and create the line element that is so common in elementary GR books, right? And that's what this is called. This is called the line element. And the line element is often very synonymously used with metric in the language of the business, and in the catalog of spacetimes it does that as well. And the reason is because if you know the line element, you can immediately extract the metric components. And if you know the metric components, you can easily create the actual metric, which is, by the way we do it, is actually a rank 2 or a rank 0 to actual tensor, right? So the components become the link between this so-called line element formalism and the metric formalism. So this is the object completely blown up by replacing all of those deltas with small differentials. And that is our definition of the line element. And you can see how the Einstein summation convention, of course, as usual, is really helpful. This all collapses to one term if you use the Einstein summation convention, right? G mu nu dx mu dx nu, right? And that is your ds squared, and that is your line element. So let's talk about how to actually use the line element to calculate a finite distance s along a path in space-time. And we remind ourselves what a path in space-time is, and I will draw an arbitrary one here. We did a lot of discussion about this in our geodesics with our, and it was pretty comprehensive. But the basic idea is we have some parameter along the path we could call tau, and we know x0 as a function of tau. We know x1 as a function of tau. We know x2 and x3 is a function of tau. And basically we've created a parameterization of the path as a function of tau. And that's what this means. Now, the idea here is that if we know a path, what that means is we know this parameterization. And that's the definition of what knowing a path is. So what this tells us is that I can write dx mu. Now, x mu now is a function of tau, and we're now understanding this is a differential, right? Not as of one form, but as a differential. Dx mu is a function of tau. It equals dx mu d tau d tau. And therefore, this part here can be written as g mu nu dx mu d tau dx nu d tau squared, right? This has always got to be squared here because there's two factors of these things. But what I've done is I've taken these two different objects, mu and nu, which could be 0 and 1 or 2 and 3 or whatever, and then we've got just one now. That's the parameterization of the path. And so now I can actually write ds equals the square root of that, and then of course this part here just becomes, when you take its square root, d tau. So the infinitesimal distance along the path is the square root of this thing with the parameterization now on the outside. And you have to be able to do this because otherwise you don't know what the path is unless you know this parameterization. And once you know the parameterization, you definitely can take its derivative and you can get this expression to be true, right? Well, to be known. And then that you can take the square root of without any problem. So a finite distance along this path, meaning the distance, say, from the start to some point, I guess the start would be tau 0 to some point tau 1, you would write s is the integral from tau 0 to tau 1 times d tau. And now that is basically how you use the line element to measure finite distances along paths in space-time. Okay, so the next thing we're going to do in the next lecture, this is long enough for this lecture, but in the next lecture what we're going to start talking about is how to take this line element and make it spherically symmetric. We're going to enforce the spherical symmetry on this body of terms. And it's going to end up, we're going to be using spherical coordinate system, and we'll start dropping certain cross terms, and we'll discover pretty quickly that the spherically symmetric metric will ultimately be a diagonal one. And then from there, we'll start talking about how these terms, these G33, G11, and G00 terms, what the most general form they can take for a spherically symmetric metric. Then once we have beaten that back and identified the spherically symmetric metric's most general form, which is pretty restrictive, then we'll start plugging those things back into this mess and start calculating this stuff in order to solve, ultimately, the Einstein equation. We'll ultimately be back here solving that thing using our spherically symmetric metric. Okay, see you next time.